In this video, we'll talk about some shortcuts to computing a derivative. In particular, we'll talk first about the power rule and the constant rule. Before we start with the actual rules, let's talk about the notation that we'll see. Now, it turns out the derivative is so important that we have many different ways of expressing the derivative of a function. So all of these expressions are equivalent. It's just a different way of expressing the idea of a derivative. That is, we can write it as f prime of x. You see the prime here. That means we're differentiating the function y with respect to the input x. Or we can be more explicit maybe and write it as dy dx. We could also write it as, well, this is called an operator in some sense. It's d dx operating on my function f. Or maybe capital D sub x onto f of x. You may even write it like this, maybe df dx, because of course we think of f, the output, as y. We call it the letter y. The first very basic shortcut rule is called the constant rule. And really it's very simple. That is that if we have a constant function is a function that is always equal to some constant. So k happens to be a real number. That is, we can write this as f of x is equal to k. That means that no matter what x is, my output is always the same. It's k. It's some particular value. We can draw a picture of that, right? That means that the function f is simply a horizontal line at the value y equal to k, right here. It means that the function does not change with changing x. It has nothing to do with x. Okay, so that means that since it's not changing with respect to x, if I want to differentiate this, the shortcut rule would say the following, that if I differentiate a constant function, no matter what, I always get 0. And why do we get 0? We get 0 because it's not changing with respect to x. Okay, it's always the same. Let me quickly prove that to you. Okay, so the proof looks like this. It's very simple. Remember that our function, which is a constant function, is just equal to k no matter what x is. And so let's just go back to the definition of derivative. Remember that it has to do with limits, ultimately. So this is a very easy proof. The derivative of f with respect to x is given by this limit, right? The limit of the difference quotient. So it's the limit as h goes to 0 of f of x plus a little bit minus f of x over that little bit, that h. Okay? So the thing about it is, remember that f of x is equal to k. Well, no matter what x is, it's always k. So for whatever input I have, it's always k. So that means that for this particular function, f of x is clearly, well, k, that's given to me. But also f of x plus h is still k because it doesn't change at all. It's always the same output. So I can rewrite that as, I'm just going to put these values into that difference quotient. I get a limit as h goes to 0 of, well, look, I've got k minus k over h. So what do? You have, well, 0. Okay, so 0 over a number is 0 always, right? So it is equal to 0. So ultimately, we've proved that the derivative of a constant is always equal to 0. The second shortcut rule we'll look at in this video is the power rule. So recall that a power function is a function that looks, well, like this. It's x to a power, where n is some real number. Okay, we're assuming that the coefficient out front is 1. So if we've got a power function, we have a shortcut rule called the power rule for power functions. So it turns out that the derivative of the power function is given by the following. What I do is I drop down this n, and I leave the base alone and reduce the power by 1. So I get n x to the n minus 1. So always the derivative of a power function is of this form for a given n, a real number, as the power of the original function. So let me quickly prove to you that this shortcut method actually works all the time. Now I'm going to simplify my life a little bit by doing this proof for n that is positive in integer. Okay, positive integers only. But this exact same procedure works for any n, any real number. Okay, so let's just have our power function here. Assume again n is a positive integer. And I'm going to, again, go to the definition of the derivative. Remember, there's a limit involved. So you've got this formula for the limit that we know about already from our definition of derivative. And I'm going to go ahead and use these values with my function. Okay, so, well, before I go any further, let's write down what this actually is. So f of x plus h, remember, I replace all of the x's with x plus h. So this is going to be x plus h to the n power. And similarly over here, well, f of x is already x to the n, so I don't have to really do anything. Now this has to be expanded, and it turns out, if you remember from the binomial theorem, expand this particular power. And so you get something like this. You get x to the n plus n x to the n minus 1 h plus some other terms all the way out to h to the n power. Okay, so there are a whole lot of terms. We start with x to the n all the way out to h to the n. Remember, sort of we move from one piece to the next, right? All of x and then all of h at the very end. Okay, all of one and then all of the other, if you remember. Okay, so let me just go ahead and expand that particular value out inside of the difference quotient here. Okay, I just want to show you this is true. So I rewrite the limit as h goes to 0 here. And I'm skipping some details, but ultimately I just want to show you this works. So there's an h down below. I'm going to replace f of x plus h by what I came up with down here. So I've got x to the n plus a bunch of stuff. N x to the n minus 1, h plus some other stuff, all the way out to h to the n minus the f of x, which is x to the n. Okay? Now, you can see already that x to the n cancels from both sides there. Then what I'm going to do is, as usual, I can divide every single term by h, right? Because it's a sum on top, so each individual piece is going to be divided by h. So what I have here is a limit as h goes to 0. This term, well, there's no more h there, so I have n, x to the n minus 1. I just divided an h out. The second term is going to be something like n times n minus 1 over 2, x to the n minus 2. There's going to be an h there. It doesn't really matter, but the point is that everything else, and of course there's h to the n, remove one of those, I have h to the n, I have one less, basically. So the whole point is that if I divide h by every term, everything has an h in it except for this first term here. Right, there it is. And that means, since we know from our definition of derivative, after I take a limit as h goes to 0, everything else is going to disappear, right? So every other term goes to 0, and all I'm left with is, in the end, when all the smoke clears, just this first term, nx to the n minus 1. And so now I've proved that, in fact, the derivative of the power function is always this result. That's our shortcut, right? That's way easier than having to do a difference quotient and limits every single time, right? I wanted to prove to you that this is how it actually works, but ultimately we don't have to do that now. Now we know the shortcut, and this is my shortcut. Now let's look at some basic examples to practice these rules that we've come up with. So remember that the derivative of a constant is just 0, and the derivative of a power is, well, we know what to do. We bring down the power in front as a coefficient, and we reduce the power left over by 1. Okay? So let's go ahead and do these two examples. So the first example, if I want to take the derivative of f, well, f is just equal to 5. Well, that's a constant, right? That means that it's not changing with respect to x. Therefore, the derivative is 0. Because remember, the derivative is measuring how much the output is changing with respect to a changing input. Okay? So I get 0. Easy enough. And the second one, again, is very straightforward because we remember our shortcut rule. That is, the power here, my n, is 3. So the derivative of g with respect to x is just bring the 3 down, leave the x alone, and reduce the 3 by 1, the power by 1, so 3 minus 1. And of course, we don't like to write it that way. 3 minus 1 is 2. So this would be 3x squared would be the derivative of x cubed. Let's look at some more examples. So here I have a function that has a fractional exponent and one that has a negative exponent. But don't worry, the procedure is exactly the same. We just follow the rule. we take the power down in front as a coefficient and reduce the power left over by 1. Okay, so let's go ahead and do that. So on example 3, I take the derivative of f with respect to x. Well, the 3/2 is going to come down. I'm left over with the x, and I have to reduce 3/2 by 1. Right? So 3/2 minus 1, well, 1 is 2/2, so you get 1/2, right? Okay, so that's the derivative. Again, all we did is we took the power down and reduced the remaining power by 1. Similarly, for the next example, if I want to take the derivative of g with respect to x, again, I bring the power down. Okay, the 2 comes down, leave the exponent alone, and I have to reduce the power by 1. But now remember, we're reducing, we're subtracting by 1, so negative 2 becomes a negative 3. Okay, so you can see that the power rule will work for any fractional power along with any integer power as well.